We have come to our last test for convergence and divergence of series. So I thought this would be a great time to review where we have been. We started off with the nth term test for divergence. We still use that. Then we went to the geometric series test, the integral test, the p-series test, direct comparison test, limit comparison test, and last time I was with you, the alternating series test. Today we are doing the ratio test. Note that there are a couple of more tests that are perfectly fine, nothing wrong with them, but College Board does not suggest or require we teach them. So I'm not going to teach those. We're just going to do these 8 tests. So today we are doing the ratio test. And the ratio test is very powerful. It is very useful. We're going to use it significantly in our next unit. This is particularly useful when a sub n has factorials or powers of n, or it's just kind of complicated. If you have a complicated expression here, the ratio test might be the best one to use. So first of all, let this series be a series of non-zero terms. So 0 is not one of our terms. The test is quite easy. The series converges if the limit of the n plus 1 term divided by the n term is less than 1, and diverges if that limit is greater than 1. If the limit is equal to 1, then the ratio test is inconclusive. We cannot use it. We must go use one of our other 7 tests. So let's see how this works with some examples. In number 1, we have this series. First of all, I would not use the nth term test because we are bottom heavy. Got Big Mama in the bottom. I already know that this is going to converge because Big Mama's in the bottom. It's extraordinarily bottom heavy. So very bottom heavy. Heavy enough to make this converge. So I already know that this converges. Let's prove it because we are told to justify our answer. So we have to prove it. We know that it's going to converge though. I want you to know that this is going to converge even before you begin. Okay, so it does have factorials. It's a little bit complicated, so I'm going to use the ratio test. The limit as n goes to infinity of, the ratio test has these absolute values, okay, which makes the ratio test very convenient to use for an alternating series, by the way. So absolute values. I'm going to start with my n plus 1 term. So I'm replacing every n with n plus 1. 2 to the n plus 1 divided by n plus 1 factorial. And now I divide by the nth term. So I'm going to divide by exactly what I see. And that's going to create a big complex fraction. Instead of writing it as a complex fraction, I'm going to go ahead and multiply by the reciprocal of the nth term. So I'm multiplying by n factorial over 2 to the n. That's the reciprocal of our, dividing by a fraction is the same as multiplying by its reciprocal. So we get this, okay? Now I need to find this limit. Before I find the limit, I'm going to reduce that expression. So I see that I have 2 to the n plus 1 divided by 2 to the n. In fact, I always have some students who want to write it like that first, 2 to the n plus 1 over 2 to the n. And then we also have n plus 1 factorial on the bottom and n factorial on the bottom, so I'm going to write that as n factorial over n plus 1 factorial. Now I'm going to reduce each piece. 2 to the n plus 1 divided by 2 to the n. The bases are the same, so we subtract the exponents. N plus 1 minus n is going to leave a 2 to the first on top, just 2. n factorial over n plus 1 factorial also reduces. N plus 1 is larger than n factorial. Remember when we did this way back when, this will be n plus 1 times n minus 1 times n minus 2 all the way down to 1. This is n times n minus 1 times n minus 2 all the way down to 1. Everything cancels except this n plus 1. So this n plus 1 will be on the bottom. So this is how that expression reduces. We have not taken a limit yet. All we did was reduce our expression. Now we're going to take the limit. Now we're going to let n go to infinity. And as n goes to infinity, the denominator goes to infinity, and the entire expression goes to 0. You're always going to be comparing it to 1. If your limit is less than 1, your series converges. If your limit is greater than 1, your series diverges. If it is equal to 1, we go use one of our other tests. 0 is less than 1. Therefore, the series converges by ratio test. Next up, number 2. Okay, quite a complicated expression. So I'm definitely going to use the ratio test. I'm going to set up the ratio test. Limit as n goes to infinity. I begin by replacing every n with n plus 1. So we'll have n plus 1 squared, 3 to the n plus 1, which is n plus 2, divided by 2 to the n plus 1. And then I'm dividing by the nth term, which means I'm multiplying by the reciprocal of the nth term. So I just flip what I see there. Okay. Time to clean up what's inside of our absolute values. And what's inside of our absolute values? Okay, let's take a look at this. I'm going to take a look at this 2 first. 2 to the n, 2 to the n plus 1. That reduces, leaving a single 2 in the denominator. A single 2 in the denominator. Okay, now let's take a look at the 3's. We have 3 to the n plus 2 divided by 3 to the n plus 1. The bigger one is on top, so I know I'm going to have a 3 on the top. How many 3's? We have n plus 1 minus n minus 1. That leaves a single 3 up on top. So just a single 3 on top. Now let's look at these n's. I've got n plus 1 squared divided by n squared. Do those reduce? No, they do not. Those do not reduce. You cannot reduce that. It just stays. Our limit will take care of that, but it stays. Okay? Cannot reduce that. All right. Now we're going to allow n to go to infinity. As n goes to infinity, I know I have this 3/2. What happens to this thing as n goes to infinity? Well, keep in mind, if we were to expand that thing, it would be n squared plus 2n plus 1. And this is just n squared. And as n goes to infinity, the 2n and the 1 don't matter, and you're left with n squared over n squared, which is 1, goes to 1. So this whole thing here goes to 1. So this entire limit is 3/2. 3/2 is larger than 1. Therefore, the series diverges by ratio test. Number 3. It's complicated. I do see a form of Big Mama on top. So since Big Mama's on top, I know that this thing will diverge. But we have to justify it. We can justify it with the ratio test. Limit n goes to infinity. Absolute values. Since it's absolute values, this -1 to the n it will make every term either positive or negative, but I'm taking the absolute value. So I can completely ignore that -1. Don't have to put it in at all. I'm just going to replace every other n with n plus 1. So this will be n plus 2 factorial divided by 3 to the n plus 1. I'm multiplying by the reciprocal of the a sub n term, so 3 to the n over n plus 1 factorial. Time to clean up. I'm not going, well, yeah, I'll write this down. Okay, so how do the 3's reduce? The 3's reduce to a single 3 on the bottom. So I know I have a 3 on the bottom. The n's reduce, the factorials reduce, I mean. The factorials reduce to an n plus 2 on top. Everything else will cancel out. Now let n go to infinity. This limit is going to infinity, which is bigger than 1 by a little bit. Therefore, the series diverges as we knew it would. And it diverges by ratio test. Let's do another. Okay, it's a little complicated. I do see a form of Big Mama in the bottom. So since she's in the bottom, I know that this thing is going to converge. We need to prove it. So I'm going to set up the ratio test. The ratio test works really well with factorials. I can ignore this -1 because of my absolute values. And I'm going to have 3 times, and I'm replacing n with n plus 1. So this is 2 times n plus 1 divided by 2 times n plus 1 plus 1. We are replacing every n with n plus 1. Multiply by exactly what I see, but flipped. Oops, 2n. Okay, time to clean it up. All right. We have in the numerator, this is 3 to the 2n plus 2. On the bottom we have 3 to the 2n. How does that reduce? Well, it reduces to 3 squared on top. Yeah? Down here, this is 2n plus 2 plus 1, so that is 2n plus 3. Factorial. How does that reduce? Well, it reduces leaving a 2n plus 3 times 2n plus 2. The next one would be 2n plus 1, but that's going to reduce with everything on top. So that is how that reduces. Now we're going to let n go to infinity. As n goes to infinity, the denominator is going to infinity. The entire fraction is going to 0, which is less than 1. Therefore, this series converges as we knew it would, this time by ratio test. Number 5. Okay, we have fairly complicated expression, so this is ideal for a ratio test. Okay. By the way, this is not geometric. We cannot use the geometric series test on this because of that n right there. I could probably mess with this and get it in the form of a geoseries. But with the n here, we cannot use the geometric series test. This is not geometric. Okay, begin by replacing every n with n plus 1. We're going to have e to the 2 times n plus 1 on top, over n plus 1 times pi to the n plus 1, which is n plus 2, times n times pi to the n plus 1 divided by e to the 2n plus 1. Okay, I'm going to clean this up. Alright, how many e's are left? Well, this thing right here This is 2n plus 2 plus 1, so that is 2n plus 3. So we have e to the 2n plus 3 divided by e to the 2n plus 1. That's going to leave me an e squared on top. On the bottom, the pi's reduce to a single pi on the bottom. The n's do not reduce. We let our limit take care of that. As n goes to infinity, this thing goes to 1 because the 1 does not matter. N's reduced to 1. As n goes to infinity, that thing goes to 1. And we are left with e squared over pi. Which is larger? We have to compare this to 1, so which is larger, e squared or pi? Well, e is about 2.7 something. Squared is going to be larger than 3.14159. So this is larger than 1. Therefore, the series diverges. By the ratio test. Next up, a very complicated expression. So absolutely we're going to use the ratio test for this one. Okay? All right. Absolute value is going to take care of that negative 1. I can ignore that one. I'm going to replace every other n with n plus 1. So 2 to the n plus 2, 3 to the 2 times n plus 1, be careful with that, divided by n plus 2, 5 to the 2 times n plus 1 plus 1, times n plus 1, 5 to the 2n plus 1, divided by 2 to the n plus 1, 3 to the 2n. Okay, we're going to have to be really careful here. I know that I can just move my n's to the back. They're not going to reduce, so I just move those to the back. I don't have to worry about those so much. Let's take a look at our 2's. We have 2 to the n plus 2, 2 to the n plus 1. The larger is on top, so I know my 2 is going to be on top. And when I subtract the powers, I'm just left with a single 2 on top. Okay, let's look at our 3's. I have 3 to the 2n plus what? Well, this is 3 to the 2n plus 2. This is 3 to the 2n. And that reduces to 3 squared on top. On the bottom, how do our 5's reduce? Well, I have 5 to the 2n plus 2 plus 1 is 3, and then 5 to the 2n plus 1 on top. That's going to leave me a 5 squared on the bottom. So this is, oh, I didn't write my n's. Let me get rid of this thing. In fact, I have some white out here. Let me get rid of that thing. Let me write my n's. N plus 1 over n plus 2. Those are going to go to 1. As n goes to infinity, this goes to 1. So I'm left with 2 times 9, which is 18, divided by 25. And 18 over 25 is less than 1. So the series converges by the ratio test. And that is the ratio test. It's a little complicated, but it is, you gotta have good algebra skills, good exponent skills, good limit skills, but that is the ratio test.